is that the rate determining step is first here, but here the rate determining step is actually the second one, and that makes a big difference to the overall rate equations. Okay.
So in the exam when doing a mechanism, you've got like actual substances. Can you substitute them so you say, for example, one particular substance equals B for the purposes of the mechanism?
No, I would just write it out. I mean, just be creative. So if you've got, I mean, you know, NO2 plus NO2, supposing that's your first step. Now just be creative, okay, let's say it makes that. I mean, I don't know if that exists, it doesn't matter. But just make it up, okay, and then you say, right, NO2, N2O4 reacts with chlorine to produce N, etc., etc., etc. That's a stupid example. Do you see my point? You just, literally, as long as you make sure the number of atoms on each side are the same, it doesn't matter if you make up molecules when you're writing an equation, a rate equation, when you're writing a reaction mechanism. It doesn't matter if you make it up. Okay. That's one of the nice things about it. It's a bit of creativity. Okay, I'm really sorry I'm going to go on a bit longer because I haven't done activation energy, have I? There's one more important thing I need to point out to you. You need to be able to do, and that is you need to be able to work out the value of the rate constant, and you need to be able to work out its units. So how would I work out the units here? I'm just going to do this one quick example. What I would say is I would say rate equals, and of course I'm taking that over to that side, so, sorry, rate constant equals rate over the concentration of those three, okay? Now, I would have values from my data, which I would then plug in, and I'd calculate the numerical value of that, Will. And how do I find out the units of the rate constant?
Take all of the units,
put all the units together, and then cancel stuff out.
Exactly. So what I do is I cancel stuff out. So what I would do is, what I've actually got on the bottom here is I've got moles per decimeter cubed, 3 concentrations, and that's cubed. Okay. So what do I do here? Well, I've got one of those on top. So what I can actually do is cancel one on the bottom, can't I? So I end up with seconds to the -1 on the top, and then on the bottom I've got moles per decimeter cubed all squared. So what would my units work out as? Well, my units there would work out as seconds to the -1, because that's on top. I've got moles squared, yes, and I bring that up to the top so it becomes to the -2. Okay. And I've got decimeters to the -6, because when you square indices you add them. Okay, so I've got because dm to the -3 squared is dm to the -6. Okay, and so because I'm taking it from the bottom to the top, it becomes dm to the 6. And so that would be my units.
Is it not the -6?
Now, no, because it was to the
No, you're bringing it
-6
to
on
the
the
top.
bottom. When I brought it to the top. Listen, please. It's the -6 on the bottom, so I brought it to the top, so I invert the sign. So those would be my units. And strictly speaking, although no one ever bothers doing this, I ought to have it in this order.
I do it in that order.
Because it needs to be in the order of the power of the indices. But don't worry.
And no one cares.
Nobody bothers.
Nobody cares.
So, yeah, you can go, yeah. Okay, the very last thing, and this doesn't take more than 5 minutes, is the very last thing is Arrhenius. Now, the Arrhenius expression, you can, the natural log of k, okay, if I take natural logs of the Arrhenius expression, I end up with this, minus EA plus natural log of A. Okay. That is the Arrhenius expression. You may have seen the Arrhenius expression in a different form. What form may have you seen it in?
To the power of what? Yeah, minus RT.
Yeah. Okay, you may have seen it like that. Now, that expression is what Arrhenius found out. He found out that when you take the rate constant, it's equal to something called the Arrhenius factor, which is a constant for every particular reaction. And that's E, that's the number E, okay, to the power of minus EA over RT, where R is the gas constant, 8.314, T is the temperature in Kelvin, and EA is the activation energy. Okay. Now, if you take natural logs of this expression, you end up with this, which is that the natural log of K equals minus EA over RT plus the natural log of A. Now that is analogous to y equals mx plus c, because what you can say is y, well y is natural log of k, okay? M, the gradient, will be EA over R times 1 over t is your x plus the natural log of A, okay? So M, x, c, y, okay? So what does this mean? Well, this is very important and very, very useful indeed. Because what it means is that you can actually, please don't, there's so much talking, okay? That if you plot a graph of yx, if you plot a graph of the natural log of k, so natural log of k on this axis, and if you plot 1 over temperature on this axis, you're going to end up with a straight line. And where it cuts the y-axis will be equal to the natural log of A. And the gradient, m, will be equal to minus EA over R.
It's a constant.
Yes.
Its value is where it is only 1.
Do I need to say that again?
Yeah.
Okay, so I'll just explain it again before you go. Right, you have the Arrhenius expression at the top, and now Arrhenius found that experimentally, by the way. He didn't like work it out and say, oh look, this is interesting, I'm going to postulate that this is the case. What he did is he did lots and lots of experiments, and he said, oh look, they seem to obey this rule. Okay, they don't all obey this rule exactly, incidentally, but he said most of them seem to obey this rule closely, based on as long as we have the following criteria, whatever, and then he said what they were. But so that expression is quite good. Okay, it works for a lot of our experiments, and that's why we use it. And then he said, look, well, if we take natural logs of this, we get this expression, and this expression can be, basically, we can plot a graph, because if you look at that, well, there we are, y equals mx plus c, we just plot a straight line graph. So all we have to do is we have to plot, on the y-axis, we plot the natural log of our rate constant. Okay, I'll go a little bit further in a second. But we have to plot, here we plot the natural log of our rate constant, and here we plot, here we plot the 1 over the temperature, and remember that has to be in Kelvin, that's very, very important, absolute temperature, otherwise it doesn't work. And we can plot a graph here, where the gradient is equal to minus EA over R. Now what does that mean? Well, it means that you carry out an experiment for a particular chemical reaction at 5 or 6 different temperatures. Okay, 5 or 6 different temperatures. You get 5 or 6 different rates, and you can calculate the activation energy. So that's really quite clever. That we can calculate the activation energy for a reaction by seeing how the rate changes with temperature.
What's EA in joules?
Well, it depends what your units are, but R is 8.314 joules per k mole, so it will be joules in this case. Now, just one thing, a very, very final thing to leave you with. The natural log of k, the natural log of the rate constant. Now the rate constant, of course, is proportional to the rate. So we can plot here the natural log of the rate, and it works just as well. Because the natural log of the rate is exactly the same. If you've got something which is directly proportional, if those things are directly proportional and you plot the natural log of them, then all that happens is the graph shifts up and down the axis. Okay? So it doesn't alter the gradient, so you can still find the activation energy even if you plot something which is proportional to the rate constant. So the reason I say that is because sometimes, and you may have done experiments in class in which you actually plotted the natural log of the rate on the axis, but it's the same. Well, it's not the same.
It works.
But I mean, it works. Okay. Now that is kinetics. And as you can already tell, hopefully, there's not a lot to learn. There's lots of practice to be done with those questions.
Except.